By definition, all building stone is durable, but it's not indestructible, especially when exposed to a harsh environment. The problem is that much of our current knowledge on building stone decay is based on research conducted in conditions that may no longer hold true.
If you go back 20 years ago when we first started, all our research was about the effects of pollution on buildings, and especially how sulphur in the atmosphere used to turn them black with soot. And then we noticed, I think about 10 years ago, that it was becoming easier to keep them clean in terms of blackness, but a lot of our buildings, especially sandstone buildings, were going green. And we made the link, and we did some research between this going green and two things. One was taking that sulphur out of the atmosphere, because the greenness is mainly algae growing on stones, and sulphur would suppress that. But also, climate scientists were telling us that our winters were likely to get longer, wetter and warmer. And this seemed to provide the kind of ideal conditions for the growth of algae and other organisms on buildings.
To find out more, the Queen's University team began devising a range of innovative research techniques, and many of them are found at this intriguing test building at Derry Gonolly in County Fermanagh, selected as one of the wettest parts of the province.
We've constructed this large hut, four-sided hut, and in each of the walls we have three different sandstones. One of them is a local stone, Dungannon, which will be very popular in the west of the province. We've got another one here. It actually comes from northwest England, but it's very similar to Scottish sandstone that's used a lot in buildings in places like Belfast. And this is one called Peakmore, which is from the north of England and is increasingly used now as a replacement stone in cities like Belfast. And what we're doing here is, on each of the four sides of this building, we're monitoring how deeply water penetrates and how long the stone stays wet.
To do this, these basic traditional building blocks are surrounded by a wealth of technical wizardry.
As you can see, we have a weather station. It monitors about 10 or 11 meteorological parameters. We have temperature and rainfall, probably the two most basic and the ones that people are most familiar with. We also have a barometer to measure pressure changes. We have an anemometer which monitors wind speed, and also a wind vane to look at the direction. And the fancy ones, sort of towards the top of the pole, they monitor radiation. So we have UV radiation. We also have global radiation, so it's able to discriminate between sunny days and overcast days. And if you monitor at a high resolution, you're also able to pick up the passing of a cloud. So it's quite detailed data.
And the technology doesn't stop there.
Here we have the moisture sensors to monitor the changing electrical properties of the stone. So we have two different types of capacitance and resistance. These are embedded at different depths. We have 5 centimeters from the surface, 15 centimeters from the surface, and 25 centimeters from the surface.
During October and November of 2010, which were very wet months, the team were able to show that a wetting front penetrated a full 25 centimetres into the stone in just 6 weeks. That's highly significant, as it has implications not only for managing decay, but for the way structures are designed.
One of the main physical effects of algae growing on the surface of stone is that it can reduce surface permeability and also keep moisture in. So we want to monitor that to see how the surface changes over time. And one of the ways that we do that is by using a piece of equipment called a portable probe permeameter. We do that by putting compressed air into these chambers, and then it moves to this gun, and software on the computer knows what the pressure in the gun is. We then fire the air into the wall, and we can get a reading of permeability as the software reads how the air pressure decays. For this real life building, we would do sort of every 6 months measure permeability to see how it's changing. Under experimental conditions in the lab, doing salt weathering trials, we would do that after every few cycles to see how the pores are filling up with salt.
The laboratory at Queen's has a wide range of technology to continue the research.
Under new environmental regimes that we associate with climate change, we expect stone blocks to be wetter for longer, and that's going to impact on how salt weathering proceeds, because we expect that if blocks are saturated, the ions will diffuse rather than moving in solution. investigating ion diffusion by this diffusion cell experiment, where we have one cell here with sodium chloride in it. In between the two cells we have a saturated stone core, and in this cell we have deionized water. And what we do is sample from this port at intervals to see how quickly the ions, the chloride ions, are diffusing from cell A through the stone to cell B.
Thanks to this close monitoring, already a number of possible strategies for mitigating climate change effects are being developed. For example, the use of biocides, water repellents, or increasing the standard thickness of building blocks. And no doubt more answers will come to light as research progresses. In the meantime, the priority is to raise awareness among architects and conservation practitioners of the likely impacts of climate change on masonry in the UK, with particular regard for the historic buildings so vital to our heritage.